chemistries that we've seen so far. Right? We've got our alkane, we've got our alkyl halides, which gave us an electrophilic carbon, which really gave us our substitution reactions. Right? Our alkenes are the next big one, and they give us two sites of reactivity, a nucleophilic carbon and a Bronsted-Lowry basic carbon, right? Which might seem a bit odd, because to be nucleophilic and basic, what do we need? Electrons, and typically we're looking for a negative. Where's the negative? Okay. We have electrons in the double bond, but we don't have a formal negative. So one of the things that we could evaluate is say, okay, well, if I don't have a formal negative, I could take those electrons and put them on one carbon, okay, which would then mean I have my formal negative. And there's my nucleophilic carbon and my basic carbon, because I've got the negative carbon. But at the same time I do that, what happens to the other carbon? Becomes positive, and we would then guess it would become electrophilic. And yet, when we look at our list of reactivities, no electrophilic characteristics. Okay? Which seems a bit odd, but it comes back to the reactivity of the alkene. When we're looking at that resonance structure, that is one way to represent it, and it is actually the worst way to represent the alkene. Why is it the worst way to represent it? Because it's charged. We should be looking at, whoops, wrong eraser. We should be looking at the neutral structure with the pi bond. That pi bond is our source of reactivity. Those are electrons. Right? So we're looking at electrons reacting. If we want to classify it as being a nucleophile, what we would be looking at is chapter, at least in our textbook, chapter 12. If we want to look at our Bronsted-Lowry basic carbon, so we want to look at it acting as a base, we're looking at chapter 11. Okay, so that's kind of our big divide between those. Same general principles apply in both circumstances. Okay, so it's just a question of what that initial first step is looking at. Some other things that might pop up when we look at our alkenes, they're sometimes referred to as olefins. You can hear terminal and internal, which referenced where the double bond was located, terminal being at the end and internal being somewhere in the middle. Okay. We could look at degrees of unsaturation, because the degree of unsaturation could be a pi bond. So there we go. That's what's happening. Okay. So degrees of unsaturation can come in when we look at pi bonds. When we look at the reactivity of pi bonds, okay, remember, we have to keep in mind our hybridization. Where are the electrons of our double bond found? They're found in p orbitals, which are located above and below, which means it can react in two different locations, which then increases the likelihood of multiple products. So we have to keep that in mind when looking at our reactions of our alkenes. Okay. Next thing I kind of want to address here, because we haven't talked about it yet, if we go over and look at our very first functional group, that very first functional group is an alkane. Kind of straightforward and boring. We didn't talk about the reactivity of those yet. We will at the end of the semester. That's looking at radical reactions. There is only one way to get alkanes to react, and that is through a radical mechanism, okay? Which kind of sucks and is cool all at the same time. Okay, so just kind of be aware of that. Last thing that we could bring in with our double bonds, we have cis-trans isomerism, so our nomenclature becomes more complex. So we have to remember that all the way back from Unit 1. Okay, so we got our same general rules for how we go through and apply those. Okay. So we got a lot of kind of bulk review information up here. Any questions about anything up there before we advance? Okay. Nomenclature, because we're now bringing in a new functional group, we should be aware of what's happening within our nomenclature. Okay. So you should go back and review. We'll look at our alkenes, and we'll also likely look at, what was that? Alkanes, always useful to remember, yep. We're going to bring in our alkyne as well. When we're looking at the addition reaction, it's not just alkenes. We're looking at the reactivity of a nonpolar pi bond. Well, alkynes are nonpolar pi bonds. There are electrons being shared between two carbons. Okay? So you need to make sure that you know how to name those carefully within those individual sections. Okay? So it should just be a general review slide. Not a big deal there. But here we run into the fun of going through and dealing with nomenclature. Okay, so let's take a minute. Should I do one for you?
Yes.
Yeah? Which one do you want to do? The ring? Okay, I heard the ring. Okay, so let's look at that ring. First place to go through and start, kind of ignore the arrow there, is identify our primary or our longest carbon chain. Our biggest group in this case is going to be that ring structure. How many carbons are in that ring structure? 7. 7 makes it a hept. It is 7 in a ring, so it should be cyclohept. Okay. Now we've got to identify our hybridization. Okay. We have a double bond, so ene. Okay. You'll notice I left a little bit of space there because depending on how we want to name, we could put our numbering for our ene in that location, or we could slide it out in front of the cyclohept. Okay. Which do you guys prefer? Okay. I heard all the way to the front. So we'll call this a cycloheptene. And then we need some numerical reference for the alkene. Okay. And let's calm down. We'll get to it. Our substituent, we have a methyl. Okay. So we have a methyl cycloheptene. Hopefully that would eliminate some answers and we could try and work our way through the rest of it. What's the next big piece of information we need to include? Where everything is located. Okay. Where does our numbering start as a general rule? At our highest priority functional group. Our highest priority functional group in this structure happens to be the alkene. So we are either starting at one or starting at one of those two carbons. Okay.
Smaller numbers.
Okay, so we could either put one here or one there. Where should 2 go? The 2 must include the other carbon of the double bond. No choice. Okay, it has to. Okay, that's the rule on how you would number. So if we started with our red number 1, that next position would be 2. Our methyl would be located at carbon 3. Okay, if we started with our purple 1, we'd have to go 2, 3, 4, 5, 6, 7, and we'd have 7 methyl. Which numbering system is correct? Okay, we want the 3 position for our methyl because lower numbers. Okay, so we end up with a name. Erase the wrong thing. Of this being 3-methyl cycloheptene, or being more specific, including the 1-cycloheptene. Okay, we don't need to include the 1 because there is only one primary functional group within there, so that 1 can become implied. Okay? And we now have the full name for that compound. Hopefully we ended up with our 5-chloropentine. And Troy, I need you to not answer this next question.
Okay.
The question becomes is, why do we call it 5-chloro? 5 is an awfully big number. Why don't we call it 1-chloro? The triple bond is our higher priority functional group. It gets the lower number. Okay. The other thing to watch out for with our triple bonds is making sure you count carbons. There's 1, 2, 3, 4, 5. So you guys picked up your 5 carbons correctly. Okay, so good job. Next group. What do we got? And sorry, this one was kind of difficult. In fact, the last 2 were kind of difficult. I apologize.
I'm going to take a whack at it. I'm not sure if I'm right. So I have 3,4-dichloro, 2-isopropane, butanol.
I see where you were going with that, but you definitely missed some. So number one, you said, let's stick with the end. You said butane, or so butenol.
Butenol.
Okay, so in your longest carbon chain, you have how many carbons? 4. But when you look, doesn't the longest carbon chain contain 5?
Yeah.
Yeah. Your longest carbon chain needs to contain the higher priority functional groups. If it does not contain the higher priority functional groups, that does not count as your longest carbon chain, which means our longest carbon chain containing our higher priority functional groups is actually right there and comes in as a 4-membered chain, which is where we get the but from, not pent. What is the hybridization of our longest carbon chain? Well, we have a double bond, so we need an ene. Okay? In this case, we will have to include the numbers in the name, in the middle of the name as opposed to out front. And that is because, what else do we have in there? We have an alcohol. So we have 2 high priority functional groups in our main chain, both of which affect the end. We have to include the naming for each of those, or numbering for each of those. Which is higher priority functional group, the alcohol or the alkene? The alcohol, so it gets the higher number. It gets, the lower number, so it gets assigned 1. The alkene shows up at position 2. Okay. As for substituents, okay, the blue ones are referenced as chloro. We have 2 of them, so we can call this dichloro. Those chlorines are located at positions 1, 2, 3. Those of you already saying 3, 4, good job. We have a 3, 4 dichloro. And then our last substituent. Okay. What did you guys run with again?
I call it an isopropane.
Okay.
Pane, sorry.
Isopropane says at the end of the structure.
Okay.
This is a substituent. How do we identify our substituents? With a YL. It's an isopropyl. Okay, an isopropyl located at which position? 2. Okay. And by all imaginations, that's where I would hope that my answer came out, and it probably wouldn't quite come out for me because there's a couple other bits of information missing. What did you suggest as another bit of information?
I'm sorry. As far as my first answer goes,
Yep.
I called it butenol.
Butene, 1-all, okay.
Yeah.
There was another bit of information that's important for this structure. Cis and trans.
Okay. I didn't
Right.
mess anything about cis and trans.
If we go through and look at our cis and trans, the chlorine is our higher priority functional group. On the left side, on the right side, where's our higher priority functional group? Carbon. Why?
Oh, you're comparing the 2 carbons.
Oh, no, wait. No, I did that backwards. Because we go out to the carbons, no difference. So then we go out to the next highest priority atom. That's where I screwed up. Okay. So our carbons first have no priority difference, so we advance. The next highest priority for the bottom one is oxygen. The next highest priority for our top is carbon. Which has higher priority? Oxygen. Sorry. Okay. Which gets us a cis. When we're looking at nomenclature, cis and trans is officially not a nomenclature system. It's a way of just kind of comparing things. So we shouldn't be using cis and trans. We need to be using E and Z. These are on the same side. We have a Z double bond located at which position? 2. So we would start our whole name off with 2Z followed by 3, 4 dichloro, 2 isopropyl, but 2 ene 1-all.
What a name.
And there it all is.
Thank you.
Okay. Again, what I would draw up is exactly what's shown up here, and then I would hope that those pieces were in there and they weren't throwing in the order of which one was supposed to happen first, because that usually confuses the hell out of me and I just accept a loss. Okay. Last thing we need to address here, isopropyl is a common name, not IUPAC. You're officially responsible for IUPAC. How can we fix isopropyl to reflect its true name? Oh crap, I needed those carbons. I also need the space though. Come on. What is the longest carbon chain? So it's still located at position 2. The longest carbon chain is a 2-carbon chain on our isopropyl group, which is known as a ethyl. Is there a substituent on that longest carbon chain substituent? Yes, there's a methyl. There is a methyl located on the ethyl group. Okay, where is the methyl located? Officially at position 1. When we're looking at naming using IUPAC, when we're numbering our substituents, they will always start at position 1 of the substituent, where it's attached to the main chain. Okay, I know is an awesome rule, and I'm sure you love that, but that's the way it runs out. How can I adjust that? Nope, I can't adjust it that way.
Bring it up slightly.
No, I can't because it's projecting into darkness. Or no, I can. Maybe I can. Never mind. I'm right. I'm wrong. There it is. 2,1-methyl ethyl. The 1, is it necessary? Technically not, so you don't have to include the 1, and in most cases I've seen people when they name IUPAC for isopropyl, they don't include the 1. It ends up getting called 2-methyl ethyl, which is exceptionally confusing because they also drop the parentheses.
And where is that supposed to be going inside of the...
Stop moving. Okay. That whole piece there replaces what we had up before, which was 2-isopropyl.
Okay.
Okay. So instead of calling it 2-isopropyl, we'd have to call it 2,1-methyl ethyl.
How would you have to use that for, like, starting the carbon chain?
I know. It pretty much breaks down to there would not be another way to go through and draw the structure. You wouldn't be able to put those pieces in appropriately.
And if 2,1-methyl ethyl shows up on the exam, do you have any preference on how we write it?
Well, you only have one exam left, which is the final. What are you responsible for? IUPAC nomenclature.
I know, but
So you should not be writing isopropyl. You need to be going with methyl ethyl.
what I was asking is, do you have any preference on how we write it as far as 2-methyl ethyl or 2,1-methyl ethyl?
Well, it's multiple choice, so there isn't a writing part to it. The way they'll typically show it is they will drop the parentheses and they'll drop the 1. And then, yeah, you'll be like, how do I get at position 2, how do I get a methyl and an ethyl? Okay? Because the 2 has to apply to only one thing. That's where the parentheses and the 1 and all that become implied.
Would the IUPAC have, by chance, confused us with maybe putting isopropyl as an option?
Yes.
And it would be wrong.
Yes.
Okay.
Sorry.
No, that's
Okay.
what.
But that's, yeah. Typically it's not the only thing wrong with it. So when they start using common names, there's something else wrong with that structure to make that name also wrong. One of the reasons why I don't like nomenclature. Okay. Last one. What do we get? How many carbons? 6. So we have a hex. I don't accept hexene. What's the issue with hexene? There's 2 of them, so I need to specify that there's 2, so it needs to be hexdiene. This is where multiple choice comes in handy. Do you need the A there? I don't know. I don't think so. I think it needs to be hexdiene. What?
I think it's hexa.
You think it's hexa? Yeah.
Hexadiene.
I'm actually not positive. That's why I would rely heavily on the multiple choice. Okay. Where are those double bonds located? 2 and 4. Whoops. And 4. Do we need to specify any extra information? Cis and trans, ultimately Z and E. Okay. What do we have? One of each. So Which one is Z, which one is E?
Which way are you now?
Depends which way you number the structure, right? Okay, if we start numbering right to left, we get Z being 2. If we start numbering left to right, we get E being 2. Well, how do we know which one's which? Nomenclature. Okay, gotta love it.
Both options be on the test?
No, I don't think they would actually test on this because I had to dig out the rule because a student actually asked me. It is rule 2.2.3, Z over E. Z takes priority. It's a 2Z 4E structure. Right? So that is rules within rules within rules to get to the level of information to appropriately name that compound.
So how would you write what these 2, C, 4, E be in the same parentheses? Or
Yes.
separate?
So when we're specifying arrangements, stereochemical arrangements, we end up using our parentheses 2Z, I already forgot, 4E. Did I do that right? Yeah. And then our I'll put in quotes, hexadiene. Okay. You do not need to specify the extra 2, 4 in there because you've already specified it within the parentheses. If there was, say, a stereocenter also in this molecule, you would include that in the parentheses list as well. Okay. So that parentheses list, depending on the complications of the structure, could be massive. And then you would follow it up with the rest of the name. Okay. Yay, nomenclature. Practice. Right? It's really all it comes down to is practice. And being meticulously careful with these. One of the things you do have to watch out for is they will do very subtle things like change the numbering of the system. Most people tend to number left to right. A very common trick is they will show the structure left to right and provide the numbering left to right, but the answer is right to left. Okay? So when you look at your nomenclature, watch out for those kind of simple traps. Okay, so we finally kind of reached a section where we can look at just massive amounts of information. Our substitution and our elimination reactions, we couldn't really just say these are all the reactions for them because there's pretty much an infinite amount of variability within the substitution and eliminations. When we move into the addition reactions, right, we can get a lot less variability, which means we can focus in on particular reagents and what they do to the course of the reaction. What you're seeing up here is what's known as a spider diagram. I picked a central molecule and then said, hey, what happens when I react it with this? What do I make? What happens when I react it with this? What do I make? Okay? So what this is intended to do is to summarize most of our addition reactions, or the reactions that we could see coming from a nonpolar pi bond. Okay? Some of these hold true for alkynes, some of them don't. Okay? So we have to be a little bit careful on that. That's where we're getting nuances within these. Some things that pop up, you'll notice, what do we have in here? Stereochemistry, so we have to watch out for it. If we move up, I guess I should star that. Okay, so we've got stereochemistry in some of these examples. But if I move up to that very next example, you'll notice, do I not have stereochemistry in that structure? There are absolutely stereocenters there. Why is it not being specified? Either can occur. Okay? I'm getting a massive weird result coming out of that. Okay? So it's too difficult for me to summarize all the possible results, so I just leave it without the stereochemistry being specified. Okay? So I tried to include a wealth of information within these structures. It can be very, very daunting to look at these. That's why you need to understand something about how each of those reactions work, which is what we're looking at in Chapter 11 and Chapter 12. Okay? If we look at kind of our bulk narrowing down of what's happening, those three reactions are Chapter 11. Sure I got that right? I think I did. Then tick, 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 tick. Here we have Chapter 12. This next one is Chapter 25. And that one I know is showing up in green, which means you can't see it, but if you watch the video, Chapter 19, I think. So I don't remember. I think it's chapter 19. What's that?
That's what it says on the PowerPoint.
It says 19?
Or the full
Okay.
chapter.
Okay, so I think that's right. The way our textbook has things organized makes it difficult to nail down where a lot of the reduction and oxidation reactions occur because of the difference in each of those mechanistic styles. Okay? So we don't see those cleanly found in one chapter, so we'll be bouncing around to cover those redox reactions. Okay? So all of these cases, what does the alkane act as? Source of electrons, every single time. Okay? Which means something about the rest of the structure or the rest of the reagents are acting as an electrophile. They need to somehow accept those electrons. And there are cases where that is obvious. Say in chapter 11, we're adding H+. What can H+ do? Accept electrons. That dictates the chemistry that's happening there. If we go through, and look at chapter 12, Br2. What does bromine typically act as when you've seen it? Okay. Leaving groups and nucleophiles. Okay, but when we're looking at Br, we're thinking about in those cases as bromide, Br minus. Is this bromide? No. Does the chemistry change?
Yes.
Massively. Okay. Everyone goes, well, why? I don't believe that. That can't possibly happen. Sodium. Ingest sodium and you're dead. Ingest sodium ion and you're alive. Okay. Very subtle changes in the electron balance within your structure makes a huge effect in the reactivity. Bromine's another one of those cases. Okay. Other ones, so you'll notice bromine shows up a whole bunch of different times because it initiates a transition state that can be very reactive. After that, we run into mercury. Mercury is really weird. Mercury is a metal. Most metals do all sorts of crazy, nasty, weird stuff when it comes to organic chemistry, which is why when we talk about simplifying the periodic table, we ignore the metals because they do crazy, nasty, weird stuff. Okay? Mercury happens to act as an electrophile and a nucleophile. Okay? Bizarre. Next one, boron. And in fact, BH3, what can you tell me about boron? It's missing an octet. Well, if it's missing an octet, what can it do? Accept electrons. There's the chemistry happening with our boron. So understanding something about our Lewis structures can allow us to predict what's happening in each of these cases. Okay? Next big thing I want to address here, you'll hear these two terms come up. Least favorite terms on the planet. Okay? Okay? Back to Zaitsev. How much did we talk about Zaitsev in class? Not really. I mentioned it, but I said it in context of form the more stable double bond. Okay? And that was where we left it. Markovnikov is the same kind of thing as Zaitsev, and everybody tries to use, oh, it's a Zaitsev product, or it's a Hoffman product, or it's a Markovnikov product. And you end up just naming a bunch of things as opposed to memorizing the chemistry of what's happening. You run into the same situation with Markovnikov. Okay? Markovnikov made a very interesting observation based on very little understanding of what was actually happening within the structures. Okay? For some reason, we then have stamped his name to it, and we keep using it. Okay? To make things more complicated, we look at the exception to Markovnikov as being anti-Markovnikov. And it's not like we've used anti already in 3 or 4 other cases that mean something entirely different than what's meaning anti-Markovnikov. Okay? So be very careful using those terms. They will pop up everywhere. Okay? I do not like them for very apparent reasons when you get into the chemistry. Okay? Next big summary slide, the alkene oxidations. Okay, these ones I'm almost positive are in chapter 19, which makes me think that our reduction wasn't. Okay? So we again start with our alkene and how can it potentially react outwards. Okay, so we'll look at some of those chemistries as well. A lot of the oxidation reactions, I know I tend to say you shouldn't be memorizing things. A lot of the oxidations are just rote memorization. Okay? We will attempt to spend some time looking at the mechanism. It's probably not worth the effort. Okay? So we'll see what happens with those. I would start spending some time getting those reagents memorized and what the end results are. Notice again, stereochemistry is popping up. Okay? Exciting, right? You now get to know how all of these pieces work. So, our addition reaction. Okay, we've got our general outline. for our reaction shown above. We're starting with our alkene, okay, and I highlighted the bond in red because that bond in red is going to act as a source of electrons, okay, which would make it a source of electrons, means it is an electron donor. If it donates those electrons to a hydrogen, we have a base. If it donates those electrons to, for lack of a better descriptor, not hydrogen, we have a nucleophile. In all cases, it can be referenced as a Lewis base. What do we need our Lewis base to react with? What reacts with bases? Acids. I need a Lewis acid. Okay. So the question becomes is what is that Lewis acid? Okay, and how does it react? In most of the cases, the Lewis acid happens to be connected to a Lewis base as well. Okay? So that when we look at the overall results of the addition reaction, we start with 2 species and we make 1. Okay? And in the result of making that 1 species, what happened to the double bond? It disappeared. Okay? It became 2 single bonds. Okay? Recognizing that pattern can help you whittle down the potential reagents to go through. When we move to chapter 11, we are very specifically changing our Lewis acid and Lewis base to being a Bronsted-Lowry acid. Okay? In chapter 12, we're going now to electrophiles and nucleophiles. Okay? Very, very specifically. How each of those reactions occur are the dynamics of looking at those individual mechanisms, but those are your general principles that are happening within those. Okay. So, here we go, our first swing. An addition mechanism using a Bronsted-Lowry acid. I want to know how you move from our reactant, the trans-alkene, to our product of our 2-bromobutane. Okay? Take a second, and actually I'm kind of curious about it. It's at least recording, maybe recording. So, 2 possible ways that we could look at this. First way, what you get, or first step, regardless of the direction that you decided to take with this, would be to identify what changed. So what changed? Double bond broke, but we've talked about this when we did the elimination reaction. Is that drawing in red in the upper left-hand corner not an equal or a valid representation of that structure? It is a valid representation of it. Is there a double bond? No. So saying the double bond broke becomes questionable, at least there. Okay? If by looking at the product we could say the double bond's no longer present. Okay? But why is it no longer present? That's your focus. Okay, so why is it no longer present? Hudson. 2 bonds formed. We have a bond to the bromine and we have a bond to a hydrogen. Okay? Those 2 new bonds have somehow appeared. For them to appear, we had to have sourced a hydrogen and bromine from somewhere, which means our reagent needs to be minimally HBr. Okay? So recognizing just what changed can possibly get you an answer. Okay? Almost guaranteed one of the multiple choice answers does not have hydrogen or does not have bromine. You just eliminated an answer choice. That's useful. Okay? So now the question becomes is how does it react? Okay? And that is a lot more of a difficult question to answer. Okay? So there are 2 approaches to this. We're forming those bonds at the exact same instant, or we're forming them at separate times. Okay? And this is going to come down to all the same concepts that we've been working at and trying to decide which one do we think should work better. If we have them happening at the same time, that means when we look at our, oops, let me use the other eraser, our HBr, it is coming down, whoops, directly on top of the double bond. The electrons from the double bond come out to react with the hydrogen. The electrons from our Br come down to react with the carbon. Yes.
Wouldn't the, it have been disassociated though, because the HBr is a strong acid?
So now we have a couple questions come up. You just said HBr is a strong acid. Well, if it's a strong acid, do I have HBr? No. So what I would have floating around in solution would be, I would actually have H plus and Br minus. So now if we go through and look at it happening at the same time, the electrons come out, the electrons come down. So, well, that looks pretty simple, right? How many species are involved in that mechanistic step? 3. H plus, Br minus, and the alkene. What are the odds we get a successful threesome? Not very good. Which means that mechanism, not very likely. The way we would decide whether it was valid or invalid is we'd go into the lab and we would test it. And we find out that that mechanism does not work. Okay? It has to be broken down into steps. So now the question becomes is what are those steps? Because I could have gone forming the carbocation, or I could have gone forming the anion. Which one was more likely? Carbocation, because electrons would repel each other. If we start putting that negative charge in there, we're saying the HBr, or the bromide, is coming in first. Well, the bromide is attacking what? It's attacking a pi bond, which is a ton of electrons. What happens when we get electrons near electrons? They repel, suggesting that our bottom mechanism is not a good choice, which then means the top one is our better option. We can follow that up with our bromide still floating around in solution, can now potentially come in and attack, and we'd end up with our final product. Make sense? Okay. So it is that kind of thought process that we've been working on throughout the semester that you need to now start doing, even with the addition reactions and reactions you have never seen. Okay? It will happen. You have to think through an approach. Does it make sense for this to be happening at the same time? Should I break this into multiple steps? What happens if I break it into multiple steps? For instance, what is interesting about the product? What is interesting in that big blue dot? It is chiral. Okay, sorry, the big blue dot may not have shown up. It was bigger on my screen. Okay, we have a big blue dot representing a chiral atom, which means we have a stereogenic center. We have wedges and dashes that need to potentially show up in this. Did we start with a chiral molecule? No. Which means our product must also be achiral. For it to be achiral, what has to happen? Both products must form. I actually have two products there. Why am I only showing one? Because I decided I didn't want to look at the stereogenic center. Okay. How do you know that you should look at it?
It gives you wedges and dashes.
Check your multiple choice answers. Do you see wedges and dashes? Then yes, you should look at it. Don't see wedges and dashes? Don't worry about it. Okay? What happens with our energy diagram? Starts at some point. Okay? So let's start our reactant somewhere in the middle because we don't know what else is going on. What then happens? Okay. It needs to go up in energy because we have charge. If we take it a step further, not only is it charged, we're actually under the octet on that carbon. Okay, so there's our carbocation. Then what happens? Okay. We neutralize our structure, so our next product should be lower in energy than the carbocation. Where should it be relative to the reactant? Why should it be lower than the reactant? No pi bond. If we go through and connect, oops, our rate limiting step ends up being the first step. What's a complication of this mechanism that we have to watch out for? Stability of the carbocation, which can be complicated because we could potentially do rearrangements. Okay? As soon as you see a carbocation, you must be thinking rearrangements.
That's the reason why I thought that the reaction happen single step instead of two steps because the carbocation was not stable enough?
Was not stable, so that then begs the question, not for this one, because here we form a secondary carbocation. Either way we react that, we form a secondary carbocation. So we'll shift to a case where we form something different and see what happens with how that reaction plays out. And we'll address that issue. Are there questions about what's up here at first? I think it's the very next slide.
Yeah, because I thought it would work better if it happened all at once than if it happened in an intermediate.
So again, it still has to happen all at once. That's three things. Likelihood of that not happening.
But it does happen.
Not with this particular molecule.
Even if you had a bunch of hydrogen,
Trying to play around with the concentration is a possibility, but it doesn't work in this case. Okay. So we end up with our final product. Okay. We already looked at our energy diagram. There's a nice pretty mechanism. Okay. For those of you that print out the slides and are like, I want that pretty mechanism, wherever you see white space, click in that white space and then press delete. Okay. It's probably because I've hidden something behind it. Okay. So in that first case, okay, what can you tell me about that double bond? Okay, for someone that happened to see the slide that I just skipped away from. Okay, yeah, it's trans, but it is symmetric. The carbons of that double bond are equivalent to each other. It does not matter where I place the hydrogen. It does not matter where I place the bromine. As long as I place them on opposite carbons, we're fine. What happens if we move to, say, some of these cases? Okay. Do I have symmetric double bonds? No. Which then means not only do I have two products, but I now have two possible sets of two products. Because I could put the hydrogen on the primary position, or I could put the hydrogen at the secondary position. So there's two possible products for that first one. For the second one, what do I get? Same deal, right? So now we run into an issue. Are those products different? Yes. So now what's going to control which product we get? Okay. It's all going to come back to that energy diagram that we just drew and I've erased. The stability of that intermediate. If that intermediate is more stable, what happens to the activation barrier? It gets smaller and that reaction goes faster. So when we go back and look at these, what is the intermediate in that first reaction? I either form the secondary carbocation or the primary, which is exactly what you were asking about. Why didn't it happen at the same time? Well, here I've got a primary carbocation. Should a primary carbocation ever form? No. Right? So to get that one to react, say I ignore the secondary possibility, how could I possibly get that to react? The only way we could potentially look at that would be doing it simultaneously. Okay? Conveniently with a double bond, there's another position that can react. Okay? Or at least in this case. And that carbocation ends up being more stable. That product is now lower in energy, and that's what drives the reaction. So I end up seeing only one product coming out of this, so one possible set of products. Okay? Why do I keep saying more than one or set? That first answer, how many products do I have there? I always have two. Okay, the bromine can either come in from above or it can come in from below in the case of our carbocation. What's the relationship between those two products? Identical. There is no chiral atom. Okay? So we have to be careful. Realize that the alkene will always have the potential of forming two possible products. You have to look at those two possible products and decide, are they the same? Are they different? Are they enantiomers? Are they diastereomers? All of that fun stuff comes back into this. When we move to the next one, what do we see in the next one? Okay, we form a tertiary carbocation. The bromine comes in from the top or the bottom. What would be the relationship between my two products? Identical, so I only see one product. And notice no wedges and dashes. Last one. Same deal, no chiral atom. I don't have to stress about it. Yes.
What about on the top right one, having a rearrangement occur?
So again, go through your intermediates. Where should the carbocation form? Left carbon or right carbon?
It's more stable in the tertiary. I would say if it did form,
What does that mean happens to the energy of that carbocation? The tertiary one goes down, the secondary is up. Which one forms?
got blasted with a bunch of lasers.
Don't make it more difficult than it already is. That would be my answer to that. Right? So, this is where Markovnikov's rule comes in. We just went through and explained the science behind this. Okay? We're forming a more stable intermediate that drops the energy of the intermediate. We get that product from that intermediate. Okay? Markovnikov didn't have electrons at that point. Okay? I think he is prior to the discovery of electrons. If he doesn't know about electrons, does he know about carbocations? No. Okay, so we can't look at this and say something about the stability of carbocations. All we can do is something about the reaction. So when he observed this, what did he look at? Okay, he looked at what was substituted in each case. The rate isn't changing necessarily for a single reaction. Okay. But he noticed when he ran this reaction that theoretically the hydrogen and the bromine should go to either position. Why is it only happening to one? Some magic must be happening there. I'm going to define a rule where my atoms are going to go to these particular locations and these particular locations only. And the rule that he came up with is that the hydrogen went where in the first structure? To that position. Hydrogen in the next structure, or the next reaction, went where? The right one. Hydrogen in the last reaction went to the right one. So he could come up with a theory. The hydrogen only goes to the right carbon. Okay, that didn't quite work because our structure can flip. Okay, so let's redefine it. Where did the hydrogen go? What is common about the right carbon in all of those? It is the least substituted. Okay. We're still thinking way back when we're looking at the Arrhenius definition of acids and bases. And in Arrhenius, we're looking at H+. The hydrogen went to the location that had more hydrogens. Okay? That is Markovnikov's rule. That's what it is. Okay? It's valid. It works. It is an observation. Okay? Does it explain anything about how or why it works? No, which is why it's a horrible thing to talk about. Okay? So when you hear people say, oh, that's a Markovnikov product, what they have attempted to do is memorize the crap out of it, and if you ask them anything to vary off of that, they will have the hardest time possible because they don't understand what's happening with the chemistry. Okay? Markovnikov is all about put the hydrogen where there's more hydrogens. All sorts of other dumb rules come out of this because some people like those memorization techniques. The rich get richer. Okay? A position that has more hydrogens will get more hydrogens in an addition reaction. Rich gets richer. Poor gets poorer. The one that had less hydrogens doesn't get hydrogen. Okay? Why does this become a mess? Because there are reactions where we start adding hydrogens to a structure that go anti-Markovnikov. It's like, oh, it's got to be something different. That's because you're looking at a stupid observation. Look at the chemistry behind it. And if you follow the chemistry behind it, the chemistry does not change. Okay? It stays the same. When we look at the reactivity of our alkene, which carbon is more negative? Let's take a look at that upper right, upper left. That's my left. Which carbon is more negative? Our blue carbon or our red carbon? Why the red one? When we look at the resonance structure, we put a negative charge on the outermost carbon. Okay, what is good about putting a negative charge there as opposed to putting the negative charge in the middle? I don't want electrons near electrons. If I look at the negative charge being on the red carbon, there's less electrons around it. That's a better place to put a negative charge. What if I look at the positive charge? There's more electrons on the blue carbon if it's a carbocation. We can use resonance to do something about predictions. To do those predictions, we have to understand electrons. Markovnikov doesn't know electrons. Stupid, stupid rule. Okay? So there's our stupid rule. Hydrogen adds to the carbon with more hydrogen. If you want to use it, by all means, go ahead. It's stupid. Yes?
How does that compare to like Zaitsev?
Right. Same kind of idea. Zaitsev just looked at forming the most substituted double bond. Well, why did we form the more substituted double bond? It's more stable. It's lower in energy. Okay? His observation was the more substituted. Okay? It is a true observation, just like when we do our acid-base reactions with Markovnikov. Okay? It is a true observation that hydrogen adds to the carbon with more hydrogen under an acid-base mechanism. What happens if we change out of that acid-base mechanism? Well, then we aren't looking at H plus anymore. We'd potentially be looking at H minus. And if I had H minus, where would H minus go? H minus would end up going to the carbocation, which is positive, our more substituted position, the one with less hydrogens. Okay? So we can come up with exceptions very quickly to Markovnikov's rule, because he only focused on a hydrogen atom. He didn't even specify whether it was positive or negative. Okay? Bad rule. Don't use it. Focus on the chemistry. The chemistry comes from resonance. Use your resonance structures to help you predict where charge builds, allowing you to go through and do an individual reaction. Okay? So, mechanistic detail. Worst case, you have no clue what's going on. Go through and look at both possible options and decide, where should I look between these two mechanisms? Okay? And decide which of those or which of those three structures should I be comparing to decide in my reaction. The intermediate, because the intermediate is charged. It's the one that's highest in energy. That's where my focus needs to be. So if I went through and drew in an energy diagram, the reactant energy for both is about the same. Product energy for both, okay, technically different because you're putting the chloride in a different location. Okay, what does the chloride have? Electrons. Where should we put electrons? Away from electrons. So if we just look at the products, which one would we expect to be lower in energy, blue or red? The blue one we might expect to be lower in energy because less electrons around it. Does that make sense? Okay. And this is where we're going to run into some interesting dilemmas here.
But the bottom would never form them because you have...
We'll address this. Okay. And we would predict both of those to be lower in energy than our alkenes. Let me draw those a little bit lower. Bi lower? Y lower? No pi bond. Where should we put our intermediates now? They should be higher than everything. Which one should be the lower of those two? Our tertiary cation should be the lowest energy, and our secondary should be higher in energy. When we go through and run the reaction, what do we end up with? Okay. And it all comes down to our slowest step. The slowest step is the formation of the carbocation, our first step. Okay? So when I look at the energy diagram, I end up seeing the red one ends up forming my product. Okay? That product is known as the... It's a tricky question. Stick with K for the moment. The other product is known as the... K and T. When have we talked about those? We'll have to end on this. I have no idea what you just said, but I think it was wrong. There it was. Kinetic and thermodynamic. All the way back to 152. Okay? How do we know which product we get? It depends on our conditions. What happens if we have a crap ton of energy in our reaction? If we provide enough energy, the kinetic product will form first. But if we provide enough energy, what can happen to the kinetic? It can go backwards. Once it goes backwards, even if it's unfavorable, I can potentially go through and now form the thermodynamic product. What happens to the reversibility of the thermodynamic product? It is not very reversible, which means once I form the thermodynamic product, I'm stuck at the thermodynamic. Okay? Huge issue in second semester. Everything we do is talk about kinetic versus thermodynamic because both are potential products. When we run the addition reactions here, we are seeing our kinetic products only. The difference in energy of our transition state is so high, our intermediate is so high, that we only see the kinetic product come out of this. Okay? And we are done there, so if you have questions,